Good morning. Welcome to join our RISC-V online bootcamp. I'm Wei-Fen, and I'm from the School of Computing International Cheng Kung University. This talk is about how we teach future computing subjects using RISC-V open source projects. I'm excited to work with the RIOS lab and its partners to promote the open RISC-V instruction set architecture and adopting its open source projects in our curriculum. RISC-V is designed to be good for all levels of computing system, from microcontroller to supercomputing. Its openness is a key enabler for its popularity in the industry. One direction for us is to make sure what we teach in school and what students will use in the industry align as much as possible. In order to give this presentation, I have talked to some professors in Taiwan about how they integrate RISC-V into their curriculum and what kind of teaching support they might need. I have collected their opinions and put it together as a summary in this presentation. Let me introduce myself. I'm currently a visiting professor at the School of Computing International Cheng Kung University. I also work for Google as a senior computer architect. My work and research interests include computer architecture, software hardware co-design, and high-performance computing. I got my PhD from the University of Michigan Ann Arbor in 2002. Before I joined the school and Google, I was the VP of Engineering in SkyMiser, Taiwan. I have great passion for education, so at my spare time, I founded a Play Lab to promote K-12 STEAM education. Another co-author of this presentation is Professor Hong Shihao from National Taiwan University. He is the CSIE Department Chair and the Deputy Director of the National Center for High Performance Computing. Professor Hong has taught computer architecture, parallel and distributed computing, and high-performance AI systems. He has been advocating for using open source projects in education for a long time. In his class, he has taught hardware-software co-optimization with open source projects, and he also conducts project-based learning with industrial collaboration. I'd like to thank him for providing his insight and help on this presentation. Here's today's agenda. I will begin with our motivations to use RISC-V open source projects in teaching. Then I will go through the current status in higher education in Taiwan. The RIOS Lab offers a small RISC-V platform. It's called PicoRIO. Besides using it in higher education, I will briefly talk about the possibility in K-12 education as well. Last, I will discuss the general feedback and suggestions collected from professors in Taiwan. So why do we embrace open source projects in education today? For schools, the most compelling reason to adopt an open source software or hardware is that it's free. But free is not just about price. It's more about freedom in sharing, learning, and collaboration. This topic has drawn a lot of attention in the open source and education community. In early August, the COSCUP 2020 conference has a dedicated track for open source education. This conference is the biggest annual conference for open source coders, users, and promoters across Asia since 2006. This year, it's the first time to have this special education track. Many educators gathered in that conference to discuss this topic, and Professor Tan from the RIOS Lab also gave a talk there. So what kind of freedoms can you have if you choose an open source project? There are 4 essential freedoms identified by the free software movement. I slightly adjusted to fit our scenario where we use not only free software but also free hardware design for education. So first, you have the freedom to run a program on an open design for any purpose. You are not limited by the license fee, royalty, or any commercial reasons. Second, you have the freedom to open up everything, look inside, study how it works from the software and hardware perspectives, and then adapt it to your needs. And then you have the freedom to redistribute software copies and hardware designs so you can help your peers. And last, you have the freedom to improve the whole program and then release your improvements to the general public so that the whole community can benefit from what you have done. With these freedoms, we believe that we can construct a better learning environment for our students. In general, we have 4 ways to adopt open source projects in higher education. The first one is to facilitate teaching using open source projects. For example, we use HackMD for document and project collaboration in the class. We also use GitLab for software development and programming assignments. As users, these tools are great for students because they are free and quite popular in the industry as well. Second, many professors use open source projects in their curriculum. For example, Linux and Android in the operating system course, GCC and TVM in the compiler course, TensorFlow and PyTorch in the AI course. If students get their hands dirty on open source projects, they can learn not just from the teacher and peers in the classroom, but also from people in the open source community, especially about the practical implementation skills which are not typically covered in the school. Once they get familiar with a particular open source project, we encourage students to be a contributor, starting from something small but interesting to them. They could ask questions on public forums and learn how to discuss with others on technical issues. Last, we might start our own open source projects for teaching and research purposes. Sometimes you just cannot find anything fit your goal, especially for emerging research topics. In that case, the best solution is to start a new one. We will have an example later. So how does RISC-V come into the picture here? Free and open source software has been a culture and movement around the world for many years. According to the Wikipedia, the open source software movement can date back to 1980s. It has been a long history, and most of open source activities mainly focus on software projects. RISC-V is an open ISA. It's the interface between software and hardware. In the past 10 years, open source hardware design becomes more popular and available as well. RISC-V drives new attention, especially with demands for more customized hardware and domain-specific computing. Nowadays, if you search the internet, RISC-V might have more open source design available than the other popular ISA ARM. In addition, you can see RISC-V in many textbooks and probably research papers as well. RISC-V is designed to be a license-free ISA. Although it's free, it has a lot of industrial-grade reference design and custom extensions. So RISC-V continues to grow its ecosystem. You can find abundant teaching materials and platforms out there. For those who like to learn hardware and software co-design, you should be able to find the resources to build a whole system by yourself. Let's share the current status in Taiwan, and I will start with the higher education. This slide shows a typical system software stack on a RISC-V based SoC. A computer science curriculum may cover many courses at each layer. For example, starting from the bottom to the top, an undergraduate program may cover computer architecture, operating system, AI applications, and software engineering. A graduate program usually covers more advanced topics such as virtual machines, AI accelerator design, system software, and advanced compiler design. Among these courses, many professors rely on open source projects for hands-on labs and final projects. I'll give you some examples. So the first example is from Professor Hongshi Hao in the National Taiwan University. He has taught a course. It's called Introduction to Open Source System Software and its Practice. In his course, 10 open source software projects and 2 open source hardware projects are included in the lectures. It gave a comprehensive overview on how to build a large system software using open source projects only. He also invited many open source project contributors and experts from different domains to cover various topics. The final project for this course covers a special topic on the RISC-V development. The operating system and the compiler topics all use RISC-V as its underlying hardware for teaching purpose. Another good example is the computer architecture course. The textbook from Dr. David Patterson and Dr. John Hennessy has a new RISC-V version since 2018. Professor Jim Huang from the CS department in our university is a very famous open source software contributor. He used 4 open source RISC-V simulators for the hands-on lab in this course. He also worked with Professor Michael Engel from Norway to port the MIT SV6 operating system to the QEMU RISC-V 32-bit emulator for teaching purpose. The simulators used by Professor Huang in the first 4 labs are for assembly programming and simple pipeline design in the entry-level course. For more advanced computer architecture course, most professors might use Gem5 for performance modeling and optimization projects. Most professors favor software simulators over hardware-based RISC-V platforms in these courses because of the following reasons. First, a budget is an issue. We might not have enough budget to buy hardware for all the students. Second, students run into more troubles with hardware and it's more difficult to arrange help for students. And the last one is the features of the hardware platform might not meet our teaching requirement. 2 weeks ago, Imagination Technologies announces a complete course on RISC-V computer architecture for undergraduate teaching as part of its Imagination University program. This course is created in association with their academic partners, Professor Sarah Harris and Daniel Sheffer. It includes an instructor's guide, a student menu, 10 comprehensive labs, test materials, sample exam questions, and all the software and hardware IPs. Some professors in Taiwan are interested in adopting some materials from this course to their own curriculum. We are looking forward to its coming release and see how it can help students to learn industrial-grade reference design. In our School of Computing, we plan to offer project-based learning courses in the future. What we have in mind is to have a course design similar to the DEC system contest. Take this year, for example. The contest is about embedded system implementation of DNN-based object detection for drones. Students receive a training data set from the industry-sponsored DJI, and the hidden data set was used to evaluate the performance of the designs in terms of accuracy and power. This is a very interesting project. In such a project, students learn a lot and they learn how to create the best performing design on an Ultra 64 FPGA board. So for RISC-V based projects, we would like to have a similar setup. Therefore, we need a similar hardware platform for students to try their ideas. Another interesting system design capstone project is to build a Beowulf cluster using low-cost RISC-V boards. The first Beowulf cluster was assembled for scientific research at NASA. But the low price to performance ratio of such clusters has opened up a new opportunity for academic institutions to build their own supercomputing clusters for teaching purpose. People have used a Raspberry Pi for such a project, and we believe that the Pico-Rio board is also great for this project as well. As I mentioned earlier, sometimes we cannot find anything that works for our project. When I plan to teach a course about AI on-chip system design, I do not have any hardware available for this course. I cannot find any open source simulator or emulator either. So 2 months ago, my friends and I have decided to start our own open source project to make a multi-core virtual platform based on another open source project, QEMU. Our plan is to have a full system emulation for the master CPU and use multi-threading programming for the subsystem modeling. We also need to get RISC-V support for QEMU from the open source community. Hopefully, this project can enable us to model various target systems in the future. So when we teach a complicated system design, we can have an emulator for students to try different ideas. Besides higher education, I think the Pico-Rio board can be used for K-12 education as well. At my spare time, I have created a lot of smart toys to teach young kids programming and how to be a maker. In Taiwan, the STEAM education is already part of the official K-12 curriculum. Many smart toys use Arduino and Raspberry Pi as their hardware platforms. I think Pico-Rio is another alternative that we can consider to use. In Taiwan, any college students can take some credit program from the education department or center and becomes a K-12 educator. They need to learn how to use this hardware and software to teach young kids. With AI applications, we need more powerful and yet low-cost hardware for K-12 education. Hopefully, Pico-Rio can outperform Raspberry Pi for this purpose. So in the last part of this presentation, I would like to share some feedback and suggestion for the Pico-Rio design. Here's the wish list from different perspectives. For software design learning, we need an alternative with different ISA. And it needs to be low cost so schools can afford it. More applications and framework supports are desired. AI applications are great examples. Of course, we need compiler and toolchain support as well. For hardware design learning, FPGA support would be nice. If we can put the whole SoC with various RISC-V implementation in a FPGA, we can teach more things in school. The board level design is better to be open sourced. We need documents or tools to calibrate power and performance. It would be nice to have multi-core support as well. For software and hardware code design, we need simulator support. Having project ideas and contests is a good way to get students more involved. In general, we are looking forward to growing a community and ecosystem for applications, documents, and tutorials. Lastly, We would like to know the roadmap of the PicoRio project so we know how to plan ahead and get involved. That's all I have today. Thank you for listening. Here's my email address. If you have any question, you are welcome to drop me a line regarding your question and comments. Thank you.